Welcome back. We're in the final video of this mini-series on CCP estimation. Our immediately prior video talked about how there's an Achilles heel with CCP estimation in that it simplifies estimation, but it does not simplify counterfactual simulations. In this video, I wanted to talk about a couple of advanced topics with CCP estimation, and that is non-stationarity of the model and what the formulas look like if our epsilons are GEV instead of type 1 extreme value. And as it relates to non-stationarity, a key advantage of finite dependence is that we don't have to impose assumptions about expectations that are far out from the current period or far into the life cycle. So in this setup, utility is actually going to vary over time now because we have a non-stationary model. You'll recall that in past videos, we've always had uj of xt. Now it's ujt of xt. The state transitions are also going to vary over time. We've sometimes put that in our models in prior videos, and sometimes we've just had fj instead of fjt. We're making decisions up until some finite horizon cap t, but we're only observing observations up until cap squiggle t instead of cap t. So if this is like a labor supply model over the life cycle, maybe we only have data up to age 30, but people are actually making decisions up until retirement age. So then a question is, what remains identifiable in this case? And there's another paper by Peter Arcidiacono and Bob Miller that goes into this in great details. I'm not going to cover that in great detail, but you can look it up. It's in Journal of Econometrics, I believe. The idea is that if we have this non-stationary environment and we have either a terminal or a renewal choice, we can identify these transition probabilities and flow utility parameters up to scale for the flow utility up until period squiggle t minus 1. And just as a review, we have the extreme value case. Again, we have the t subscripts on the u and the f. But if we have type 1 extreme value, then we're going to have the log of the sum of the exponentials of the conditional value functions in the future period. And then as a review, we did the multiply divide by the same component trick here. And that got us this formula here. So this is big V, and we know that big V is equal to little v j minus log of pj for any j. And then the beta times Euler's constant is just going to go away once we look at choice probabilities because it's common to every option. Or we can think of it differencing out if we take the differenced conditional value functions. And the important thing to know is that this expression holds regardless of expectations in t plus 2. So that's the key idea here, that we don't need to make assumptions about what's being expected far out into the future. Now, what if we have finite dependence that's more than one period ahead? In this case, we can still have time variation in the transition functions, but we need to have stability in the utility function. So we can have non-stationary transition functions, but we need stationary utility functions. And the reason for that is because we have future utility terms in our model that we don't have data on, but that we need data on in order to estimate. In any case, all of what I've just described so far implies that we can estimate non-stationary games. What are games? Well, it's an application of game theory, so maybe there's firms that are competing in some game theoretic manner. We can have that be a non-stationary setting and still recover the parameters given what I had just told you. This is not of particular interest to my research, but it might be to yours, and so I wanted to at least cover it. Now let's shift gears and talk about what happens if the epsilons are GEV instead of type 1 extreme value. And the idea is that we can still express big Vt plus 1 in a closed form because of the McFadden theorem that we went over several mini-series ago. However, it gets more complicated because that g function that McFadden derived can get quite complicated. So the exact math is going to depend on the form that this g function takes, but at least we know that big Vt plus 1 is equal to log of g. And so for the nested logit, we're going to have these nest correlation parameters, the lambdas that we talked about in earlier videos. If the epsilons are normal, this big Vt plus 1 is not going to have a closed form expression. And so we're going to need to do some kind of simulation to compute that Emax integral. So maybe it's Monte Carlo integration that we talked about in a prior video, or some other approach. But the point is we can still use CCPs even if the epsilons are normal. It just might not actually save us all that much computation time if the integral is taking just as long as it would to solve the model fully, for example. Let's go through the exact math for the nested logit case. I have any number of nests indexed by R, and then within each nest, I have J that's in capital J sub R as the alternatives that are in nest R. And then I have my lambda R, which is a different lambda for every nest in my model. And I'm going to index G by T just to emphasize that all of this stuff depends on the state xt. So if we recall from prior videos, what's the probability of choosing option J if it's in nest R? Well, it's going to be this formula that we got from the McFadden theorem. And then I can also think about the probability of choosing nest R, which is just this component without the -1 power on lambda. And so that's just a little bit of a review from past videos. There's nothing new here. This is the total probability that I choose nest R, and then this is the individual alternative probability that I choose option J that's in nest R. And I apologize for the notation here. This should just be nest R, or this could be nest JR. And, hopefully you understand what I'm getting at. So this nest probability can take that, so we can multiply G times that nest probability, raise it to the 1 over lambda R power, and that would just give me this component, which is basically what's the conditional value function for all the alternatives in the nest. So it's like the numerator of that nest probability. And then I can substitute that into the choice probability to get this formula. And then if I simplify, then I get that the choice probability is a function of the denominator times the nest probability times this other term. That's like an exponentiated utility. So this basically, why did we want to express it in this way? Well, it's helpful because we're going to need something like log of pj to do the CCP, but it might be a function of the nest probability and some other stuff. So I can take logs of both sides and rearrange terms, and I can eventually solve that my log of G is a function of my log of P and my log of the nesting P, as well as my conditional value function. So this is kind of like the psi term in our new model with the GEV errors. So in the past, we had Vj minus log of Pj, right? And I will get that if I set lambda equal to 1. But we know that big V is equal to log of G plus Euler's constant. And so we're basically done with what we need to do CCPs with a nested logit model. And as I just said, if we set lambda R equal to 1, then this is going to reduce to the simple IID logit case. This was what we did for the nested logit. Now what do we do for GEV? Well, that's going to be more difficult because it depends on the form of the generator function that we take. We might have cross-nest probabilities in here if it's an overlapping nests model, and so on and so forth. However, if we have a particular state, we can numerically solve for big VT because we have this formula that the probability is equal to the partial derivative of the log of G with respect to the argument that I want, the little vj. So I can stack this for all choices and then just solve. I have a system of j-1 equations, and I can numerically solve for it that way. So it's not going to have a closed form solution necessarily, depending on what the exact G function looks like, but it is going to be numerically solvable, this is going to be a lot less computationally intensive than using simulation to approximate an integral, for example, like we would if we had a normally distributed epsilon. That is it for this mini-series on conditional choice probability estimation. I hope you've learned some valuable skills and picked up some tools that you can use in your research. If not, that's all right. I hope you enjoyed learning about something new and a way that we can simplify the estimation of the parameters in a dynamic discrete choice model. Thanks for joining, and I hope to see you in the next series.